This creates chronic low-grade ischemia. Tissue survives, but under metabolic strain. Oligodendrocytes responsible for maintaining myelin become less efficient. Axonal repair weakens. Inflammatory signaling increases around compromised vessels. White matter integrity slowly fragments, while outward neurological function remains mostly preserved. The first consequence is not usually paralysis. It is slowing. Signal transmission across distributed systems becomes less synchronized because vulnerable pathways cannot sustain normal conduction speed consistently. The person may still complete tasks successfully, but processing efficiency gradually declines. Lacunar infarcts accelerate this deterioration. These tiny strokes occur when small penetrating arteries become obstructed deep inside the brain. Individually, many are too small to produce dramatic symptoms. Some occur without the person noticing anything abnormal at all. The danger comes from accumulation. Each microscopic infarct removes a small portion of network connectivity. One lesion may slightly weaken motor timing. Another may disrupt attentional regulation. Another may impair emotional filtering. Compensation hides the deficits initially because surrounding circuits redistribute workload. Over years, however, the cumulative burden becomes impossible to conceal completely. Communication systems that once operated smoothly begin showing widespread inefficiency. The brain loses integration before it loses raw survival capability. Vascular dementia often progresses through this mechanism. Unlike Alzheimer's disease, which initially targets memory systems more selectively, vascular degeneration disrupts distributed connectivity across multiple domains simultaneously. Attention, processing speed, executive function, emotional regulation, and motor coordination may all deteriorate together in fragmented patterns. This fragmentation reflects network instability rather than isolated regional collapse. The brain is still receiving information, generating thoughts, and producing movement, but communication between systems becomes increasingly unreliable. Signal timing is especially sensitive to vascular compromise. Neurons can tolerate brief reductions in efficiency better than they can tolerate synchronization loss. A delayed signal arriving milliseconds late may still produce movement, but coordination precision begins deteriorating. Walking demonstrates this clearly. Locomotion requires constant interaction between sensory feedback, cerebellar correction, motor planning, vestibular balance systems, and spinal coordination pathways. Microvascular white matter damage weakens synchronization between these systems before muscular weakness becomes obvious. The result is subtle gait slowing, shortened stride length, delayed balance correction, or instability during directional changes. These signs often appear years before severe disability because compensation initially absorbs much of the disruption. Processing speed throughout the brain also slows under chronic ischemic stress. Conversations requiring rapid attention shifting become mentally exhausting. Complex decision-making takes longer. Unexpected environmental changes produce disproportionate cognitive overload because communication pathways are operating with reduced reserve capacity. This slowing is frequently mistaken for ordinary aging. The person still remembers familiar information and performs routine activities independently. What disappears first is efficiency, not existence of function. Microvascular damage also weakens emotional regulation indirectly. Frontal subcortical circuits depend heavily on intact white matter communication. As these pathways fragment, emotional filtering becomes less stable under stress. Irritability, apathy, emotional exhaustion, or reduced frustration tolerance begin appearing gradually. Because symptoms emerge slowly, behavioral explanations often replace neurological ones. Family members may attribute changes to personality, retirement, stress, sleep problems, or mood disorders. Meanwhile, the structural infrastructure supporting emotional regulation is steadily deteriorating beneath the surface. The brain attempts to compensate continuously. Neighboring vessels dilate to improve local perfusion. Surviving pathways increase recruitment. Cortical regions expand activation during tasks requiring concentration. For a time, these adaptations preserve outward independence remarkably well. Compensation has metabolic consequences. Increased neural recruitment raises oxygen demand precisely when vascular delivery is already compromised. Regions surviving near their metabolic threshold become increasingly vulnerable to additional stressors such as infection, dehydration, poor sleep, or blood pressure fluctuations. This explains why individuals with significant small vessel disease often experience fluctuating function. One day cognition feels relatively stable. Another day produces severe mental slowing or imbalance without obvious external cause. The underlying network is operating near failure thresholds where small physiological changes produce disproportionate effects. Comparison with acute stroke reveals how deceptive chronic vascular degeneration can become. A major stroke forces immediate recognition because function disappears suddenly. Small vessel disease destroys connectivity incrementally enough for adaptation to continue masking progression. The slower the injury develops, the more effectively the brain hides it. That concealment allows structural damage to accumulate across decades before severe disability becomes undeniable. Eventually, however, network fragmentation reaches a critical threshold. Compensation systems begin interfering with each other instead of stabilizing function. Attention deficits worsen motor coordination. Cognitive fatigue worsens emotional regulation. Slowed processing increases balance instability. Previously isolated inefficiencies merge into system-wide decline. At this stage, the problem is no longer localized vascular injury. Entire communication architectures are destabilizing together. White matter pathways carrying information between frontal, sensory, emotional, and motor systems lose synchronization across multiple domains simultaneously. The person may still appear functional during brief interaction because routine behaviors remain preserved longest. Under sustained demand, however, the hidden instability becomes harder to suppress. Mental endurance collapses earlier. Adaptation slows. Recovery from stress takes longer. Microvascular destruction is dangerous precisely because it rarely announces itself dramatically at the beginning. It removes connectivity silently, one microscopic injury at a time, until the brain eventually reaches a point where compensation can no longer keep the system synchronized. Memory failure rarely begins with forgetting names or becoming lost. The earliest damage develops much deeper inside the mechanisms responsible for encoding, stabilizing, and retrieving information, long before obvious forgetfulness appears externally. The hippocampus plays a central role in this process. Located deep within the temporal lobes, it helps convert short-term experience into stable long-term memory through continuous synaptic reinforcement. Every new conversation, location, instruction, and sequence depends on hippocampal networks integrating incoming information with existing neural patterns. Early degeneration does not immediately erase stored memories. Instead, it weakens the efficiency of encoding and retrieval pathways. The person still recognizes family members, remembers important life events, and maintains familiar routines. What begins failing first is the reliability of transferring new information into stable long-term storage. This distinction matters because preserved old memories create the illusion that memory systems remain healthy. A person may speak fluently about events from decades earlier, while repeatedly losing track of recent conversations or new instructions. The storage architecture is becoming unstable, even though older consolidated memories remain accessible. Alzheimer's disease often begins through this hidden progression. Abnormal accumulation of beta amyloid and tau pathology disrupts synaptic communication years before severe cognitive symptoms emerge. Neurons initially survive, while their signaling efficiency gradually weakens. The earliest consequence is not total amnesia. It is fragmentation of memory consolidation. The brain struggles to stabilize newly acquired information because hippocampal circuits can no longer coordinate synaptic reinforcement with normal precision. At first, these disruptions are subtle. A person rereads the same paragraph repeatedly because retention weakens between moments of attention. Conversations require increased concentration to follow continuously. Recently learned details fade faster than expected despite preserved intelligence. Compensation conceals much of this instability. Frontal executive systems increase conscious effort during recall. Contextual cues and habit patterns help reconstruct missing information. Family members often interpret the changes as distraction, stress, or normal aging because outward function remains largely intact. The brain also prioritizes emotionally reinforced and repetitive information. Frequently used memories survive longer because repeated activation strengthens distributed cortical storage networks. This is why highly familiar routines may remain preserved despite progressive hippocampal deterioration. A person can still drive a familiar route, prepare routine meals, or discuss well-rehearsed topics while struggling to retain recent instructions or unfamiliar details. Procedural memory systems remain relatively stable longer than flexible episodic encoding systems. Retrieval failure and storage failure are not identical. During retrieval failure, information exists, but access becomes temporarily inefficient. During storage failure, the memory trace itself was never stabilized properly. Early neurodegeneration often shifts gradually from retrieval instability toward true consolidation impairment. The transition is difficult to recognize because intermittent successful recall creates the impression that memory remains intact. The person occasionally remembers correctly, reinforcing the belief that failures are caused by stress or distraction rather than structural degeneration. Sleep becomes critically important during this stage. Memory consolidation depends heavily on coordinated hippocampal cortical activity during deep sleep cycles. Neurodegeneration disrupting these synchronization processes weakens overnight stabilization of new information. Poor sleep, therefore, amplifies memory instability disproportionately in vulnerable brains. Information that might previously have consolidated successfully now decays before long-term storage can occur. Fatigue further reduces attentional encoding efficiency during waking hours, creating a reinforcing cycle of cognitive decline. Signal timing again becomes central. Memory is not simply stored in one location. It depends on synchronized activation across distributed cortical networks. White matter deterioration slows communication between these regions, reducing the precision required for rapid retrieval and integration. A conversation demonstrates this dependency clearly. Understanding speech requires auditory processing, language interpretation, working memory maintenance, emotional context evaluation, and response planning simultaneously. Degenerating communication pathways increase the effort required to maintain this synchronization. The person may appear mentally present while internally struggling to preserve continuity between incoming information and short-term retention. Moments of conversational drift become more frequent. Details disappear between sentences. Context must be reconstructed repeatedly during interaction. Microvascular disease intensifies these problems by reducing perfusion to white matter pathways, supporting memory integration. Small ischemic injuries disconnect communication between frontal executive systems and temporal memory structures. The result is slower retrieval, weaker organization, and reduced attentional stability. Inflammatory signaling also contributes directly to synaptic dysfunction. Activated microglia surrounding degenerating tissue release cytokines, altering neurotransmitter balance and weakening synaptic plasticity. Memory systems lose adaptability before large-scale neural death occurs. At this stage, the person often develops compensatory behaviors unconsciously. Notes become more necessary. Repetition increases. Structured routines reduce reliance on flexible recall. Familiar environments feel safer because they minimize cognitive demand on unstable encoding systems. The danger is that successful compensation delays recognition of progression. The brain still produces coherent conversation, recognizable personality, and functional independence. Internally, however, reserve capacity is steadily shrinking. Temporal sequencing becomes increasingly fragile as degeneration spreads. The person may remember isolated facts while losing accurate ordering of events. Conversations blend together. Repeated questions emerge because previous interactions were never consolidated into stable memory traces. This fragmentation reflects weakening network integration rather than isolated forgetting. Memory systems require precise interaction between hippocampal encoding, frontal organization, attentional filtering, and cortical storage. Degeneration slowly destabilizes all of them together. Emotional interpretation also changes during this process. Familiar people remain recognizable longer than contextual details because emotional recognition pathways partially compensate for declining episodic memory. The person senses familiarity while losing precise informational continuity. That mismatch creates confusion difficult to describe internally. The world feels recognizable but increasingly unstable. Cognitive effort rises continuously as the brain struggles to maintain orientation using incomplete information. The most dangerous aspect is that memory decline begins long before obvious dementia appears externally. Structural degeneration may already be extensive by the time family members recognize persistent cognitive failure. Years of microscopic synaptic disruption, white matter instability, inflammatory stress, and metabolic compromise often exist before diagnosis becomes unavoidable. By the time visible forgetfulness dominates daily life, the underlying disease process has usually been progressing silently for a very long time. One of the most deceptive features of neurodegeneration is that the body can continue moving long after the systems controlling movement have already begun failing internally. Automatic behaviors survive because the brain prioritizes preservation of essential motor patterns even while higher-order coordination networks deteriorate. Walking is heavily automated inside the nervous system. Once learned, locomotion depends on deeply reinforced circuits involving the basal ganglia, cerebellum, brainstem, spinal pattern generators, and motor cortex. These systems allow repetitive movement to continue with minimal conscious control. This preservation creates a dangerous illusion. A person may still walk independently, while the neural architecture responsible for precise movement regulation is already under severe strain. The body appears functional because automatic motor programs remain active. The basal ganglia play a central role in this concealment. These deep brain structures help initiate movement, regulate motor fluidity, suppress unwanted activity, and automate repetitive actions. During early degeneration, surviving dopaminergic systems compensate aggressively to preserve visible movement stability. Parkinsonian disorders demonstrate this clearly. Long before severe tremors or rigidity appear, dopamine-producing neurons inside the substantia nigra may already be substantially depleted. The nervous system initially responds by increasing dopamine utilization efficiency and recruiting additional cortical involvement during movement. The person continues functioning because compensation temporarily stabilizes output. Internally, however, movement is becoming increasingly dependent on conscious effort rather than automatic coordination. One of the earliest hidden changes is reduced movement spontaneity. Facial expression becomes less dynamic. Arm swing during walking decreases subtly. Movement transitions require slightly greater mental initiation. These signs emerge before obvious weakness because initiation systems destabilize earlier than muscle activation itself. The body still moves, but fluidity begins disappearing underneath the surface. Upper motor neurons and lower motor neurons illustrate another critical distinction. Upper motor neurons originate in the brain and coordinate voluntary movement planning. Lower motor neurons directly activate muscle fibers. Degenerative diseases affecting these systems create different progression patterns depending on where transmission failure begins. Amyotrophic lateral sclerosis exposes this interaction dramatically. Early ALS may begin with small motor inconsistencies rather than complete paralysis. Fine hand coordination weakens. Speech articulation fluctuates. Muscle twitching appears intermittently. The muscles themselves initially remain capable of contraction. The problem begins inside motor neuron degeneration, disrupting command transmission reliability. Signals arriving from the cortex become fragmented as upper and lower motor pathways progressively deteriorate. Compensation delays visible collapse here as well. Surviving motor units expand their workload by innervating additional muscle fibers temporarily. Strength appears preserved even while motor neuron loss continues progressing underneath. This adaptation has limits. Enlarged motor units become metabolically overburdened and increasingly unstable. Fatigue worsens transmission consistency. Precision disappears before total strength vanishes. The nervous system also prioritizes preservation of habitual movement patterns over novel actions. Familiar repetitive tasks remain functional longer because they rely on deeply reinforced circuitry requiring less dynamic processing. A person may still walk through familiar environments while struggling with sudden directional changes, obstacle navigation, or multitasking during movement. Automatic motor programs survive. Adaptive motor flexibility weakens. This distinction becomes visible during divided attention. Healthy motor systems coordinate automatically with minimal conscious supervision. Degenerating systems increasingly require executive oversight to maintain stability. Walking while conversing becomes harder. Turning quickly during distraction produces imbalance. Complex hand movements during cognitive stress lose coordination. The body can still move, but movement is no longer operating with normal reserve capacity. Cerebellar correction systems attempt to compensate continuously. The cerebellum monitors incoming sensory feedback and rapidly adjusts motor output to maintain smooth coordination. As upstream signals become less reliable, corrective workload increases dramatically. This additional burden eventually exposes instability during fatigue or stress. Movements overshoot slightly before correction occurs. Balance recovery slows after minor disturbances. Speech rhythm becomes uneven during prolonged conversation. Signal timing is again central to the problem. Muscles do not require only activation. They require synchronized activation and inhibition across multiple groups simultaneously. Degenerating pathways disrupt this timing precision before movement disappears entirely. Fine motor tasks reveal this instability earliest because they depend on exact sequencing. Handwriting changes subtly. Buttons become harder to manipulate. Finger coordination during typing becomes inconsistent. These failures often fluctuate because compensation still partially succeeds. The person experiencing them may dismiss the changes because overall functionality remains preserved. The nervous system continues generating enough successful movement to maintain independence while hidden strain increases internally. Microvascular disease worsens this progression by damaging white matter tracts connecting frontal planning systems with motor execution pathways. Communication delays spread through distributed motor networks. Processing speed slows. Corrective timing weakens. At the same time, executive fatigue reduces attentional resources available for compensation. Tasks previously handled automatically now consume conscious concentration. Long periods of movement become mentally exhausting because the brain is actively supervising functions that once required minimal oversight. The disconnect between appearance and structural reality grows larger as degeneration advances. Observers see preserved movement and assume preserved neurological stability. Internally, however, surviving circuits are operating near metabolic exhaustion to maintain ordinary behavior. Speech demonstrates this contradiction clearly. A person may still communicate fluently overall while microinstability spreads through respiratory coordination, tongue movement timing, facial activation, and language integration pathways. Minor pauses, slurring, or irregular pacing emerge before obvious speech collapse occurs. These signs are often intermittent because compensation fluctuates according to fatigue, emotional stress, sleep quality, and metabolic demand. The inconsistency itself becomes misleading. Temporary improvement creates the illusion that the problem is reversible. Neurodegeneration does not require complete system failure to become dangerous. It only requires enough instability to reduce reserve capacity below what daily life demands consistently. Eventually, automatic systems can no longer fully conceal the deterioration. Conscious effort increases continuously, while movement reliability decreases gradually. The body still moves, but the networks sustaining that movement are becoming increasingly fragmented, inefficient, and metabolically unstable. There comes a point when the brain can no longer distribute enough compensation to keep deterioration hidden. The transition is rarely sudden at first. Small failures that once appeared isolated begin overlapping across multiple systems simultaneously. Movement, speech, attention, emotional regulation, and sensory interpretation start breaking down together instead of independently. Visible tremors often emerge during this stage because inhibitory motor control weakens beyond compensatory capacity. Healthy motor systems constantly suppress unnecessary movement through coordinated basal ganglia regulation. As dopaminergic pathways deteriorate further, suppression becomes unstable. The tremor itself is not random movement. It is evidence that competing motor signals are no longer being filtered correctly. Muscles receive oscillating activation patterns because synchronization between excitatory and inhibitory circuits has fractured. At first, the tremor may only appear during rest or fatigue. Stress amplifies it because compensation requires additional cortical recruitment and neurotransmitter demand. The nervous system can no longer stabilize movement automatically under increasing physiological burden. Speech also becomes harder to conceal. Early pauses and timing inconsistencies evolve into visible articulation instability. Respiratory coordination, tongue movement sequencing, vocal modulation, and language planning begin interfering with each other as distributed communication networks lose synchronization. Words may still be correct, but delivery becomes effortful. Sentences fragment under cognitive load. Speech volume decreases because automatic motor regulation weakens. The person may appear mentally slowed when the deeper problem is unstable integration between multiple neurological systems. Signal execution delays become more obvious during movement initiation. The intention to move remains intact, but the transition from planning to action slows noticeably. Standing up, turning, beginning to walk, or changing direction may briefly freeze before movement resumes. This freezing reflects widespread communication instability rather than muscular weakness. The command exists. The muscles remain structurally capable. The failure occurs during network coordination between frontal planning systems, basal ganglia initiation circuits, cerebellar timing pathways, and spinal execution networks. Sensory interpretation also begins deteriorating more visibly. Vision itself may remain normal, while spatial processing becomes unreliable. Crowded environments become disorienting because filtering competing sensory input requires precise frontal coordination that weakened white matter pathways can no longer sustain efficiently. The person may feel overwhelmed by noise, motion, or rapid environmental changes. This is not simple distraction. It is reduced network capacity to integrate simultaneous sensory information without cognitive overload. Executive systems become increasingly unstable under pressure. Tasks requiring rapid adaptation expose deficits clearly because compensation no longer has sufficient reserve capacity to reorganize effectively. Unexpected interruptions, multitasking, or emotional stress trigger disproportionate breakdown in performance. Family members often notice that the person functions relatively normally during familiar routines, but deteriorates rapidly during complex or unpredictable situations. Structured repetition still survives. Flexible adaptation weakens. Cross-layer collapse becomes unavoidable during this stage. Cognitive slowing worsens motor instability because delayed processing disrupts corrective timing. Emotional stress worsens attentional control because frontal inhibitory systems are already metabolically strained. Fatigue worsens speech coordination because compensatory recruitment can no longer sustain continuous high-demand activity. Previously separate inefficiencies begin amplifying one another continuously. Microvascular disease accelerates this threshold effect. Chronic white matter fragmentation reduces communication reliability across entire neural networks. When additional degeneration develops on top of this instability, compensation systems lose the ability to synchronize effectively. The nervous system begins prioritizing basic survival behaviors over precision. Gross movement may remain possible while fine coordination deteriorates sharply. Simple conversation survives while rapid processing collapses. The brain preserves core functionality by sacrificing efficiency and adaptability. At this stage, internal awareness often begins increasing. Earlier in progression, impaired self-monitoring systems prevented accurate recognition of decline. As failures become more visible externally, the person may finally recognize that something deeper than stress or aging is occurring. This realization can be psychologically devastating because the symptoms now reflect years of hidden progression already completed internally. The visible breakdown is not the beginning of disease. It is the point where compensation finally became insufficient. Reaction speed slows across nearly every domain. Conversations require more processing time. Motor adjustments occur later. Emotional recovery after stress becomes prolonged. Decision-making under pressure becomes unstable because synchronization between executive and sensory systems weakens continuously. The cerebellum attempts to preserve coordination through increased corrective signaling, but delayed incoming information limits accuracy. Movements become less fluid because feedback arrives too slowly for seamless adjustment. Balance instability becomes harder to hide. Minor perturbations that healthy systems correct automatically now require conscious attention. Uneven surfaces, directional changes, or simultaneous cognitive tasks expose coordination deficits more clearly. Falls become increasingly dangerous because delayed corrective responses reduce the ability to recover rapidly after loss of balance. What once would have been a harmless stumble becomes a neurological timing failure with physical consequences. Memory systems also deteriorate further under growing network instability. Retrieval delays merge with encoding weakness. Conversations repeat more frequently because attentional fragmentation prevents stable consolidation during interaction. Emotional regulation weakens substantially as frontal limbic communication pathways lose synchronization. Frustration tolerance narrows. Anxiety increases because unpredictable cognitive and motor instability creates continuous uncertainty inside daily life. The body still appears alive and active, but internal reserve capacity is disappearing rapidly. Every movement, conversation, decision, and sensory interpretation now consumes disproportionate neural effort. The brain can no longer hide the damage because too many systems are failing together at the same time. There is a critical difference between neurons that are temporarily impaired and neurons that are permanently destroyed. Early in neurodegeneration, many pathways still survive in weakened form. Signals slow, fluctuate, or fragment, but some degree of transmission remains possible. Irreversibility begins when structural destruction exceeds the nervous system's ability to maintain functional connectivity at all. Dead neural tissue does not regenerate the way skin or blood cells regenerate. Mature neurons within the central nervous system possess extremely limited replacement capacity. Once large numbers of neurons die, the communication architecture they formed begins collapsing permanently. The mechanism of neuronal death varies depending on the disease process. Chronic ischemia deprives tissue of oxygen and glucose until metabolic failure destroys cellular integrity. Excitotoxicity floods neurons with excessive calcium signaling, triggering destructive enzymatic pathways. Protein aggregation disrupts intracellular transport and mitochondrial function until the cell can no longer sustain itself. Regardless of the pathway, the consequence is the same. The neuron stops participating in network communication permanently. At first, surviving systems attempt compensation again. Neighboring neurons strengthen existing synapses. Alternative pathways increase recruitment. Cortical regions redistribute workload to preserve fragments of lost function. Neuroplasticity delays complete collapse even during substantial tissue loss. Plasticity has biological limits. It can reorganize surviving circuits. It cannot fully replace destroyed large-scale architectures once enough connectivity disappears. Glial scarring becomes part of this irreversible transition. Astrocytes surrounding damaged tissue proliferate to stabilize the injured region and contain inflammatory spread. This response protects neighboring structures from acute injury expansion, but it also creates dense scar barriers, disrupting future reconnection. The scar tissue itself does not transmit neural signals normally. Communication pathways crossing the damaged region become fragmented or permanently interrupted. The nervous system loses integration, even if surrounding tissue remains partially alive. White matter degeneration amplifies this disconnection dramatically. Axons linking distant cortical regions deteriorate alongside neuronal loss. The brain no longer fails only at isolated processing centers. Entire communication systems become anatomically disconnected. This is why advanced neurodegeneration affects multiple domains simultaneously. Movement, speech, emotion, memory, and autonomic regulation all depend on integrated network coordination. Once enough connectivity disappears, dysfunction spreads system-wide rather than remaining localized. Functional ceilings emerge during this stage. Early compensation depended on reserve capacity and redundant circuitry. As tissue loss progresses, remaining networks operate continuously near maximum workload. There is no longer enough healthy reserve available to absorb additional stress. Fatigue becomes severe because ordinary activity consumes disproportionate metabolic resources. Small physiological disturbances that healthy brains tolerate easily now trigger major functional decline. Infection, dehydration, emotional stress, or sleep disruption can produce dramatic worsening because the nervous system no longer possesses stabilizing capacity. The difference between temporary inflammation and permanent loss becomes increasingly obvious. Earlier in disease progression, symptoms fluctuated because conduction instability varied according to physiological conditions. During irreversible degeneration, deficits persist even during ideal conditions because structural architecture itself has disappeared. A hand no longer weakens only during fatigue. It remains weak continuously because motor neurons controlling precise movement have died. Speech no longer fluctuates unpredictably. Articulation remains impaired because integrated motor sequencing pathways can no longer synchronize effectively. ALS demonstrates this transition with devastating clarity. Surviving motor neurons initially compensate for neighboring cell death by expanding motor unit coverage. Eventually, neuronal loss becomes too extensive. Compensation collapses abruptly because remaining cells cannot sustain the workload required for functional preservation. Muscles begin atrophying, not because they are inherently diseased first, but because denervation removes the neural signals required to maintain muscular integrity. The body loses movement because the communication system controlling it no longer exists. In Alzheimer's disease, irreversible progression appears differently. Massive synaptic and neuronal loss gradually destroys distributed cortical networks responsible for memory integration, orientation, language coordination, and executive control. The person does not simply forget information. The architecture required to organize conscious continuity itself begins disintegrating. Recognition systems fragment. Temporal sequencing collapses. Environmental interpretation weakens. The world becomes increasingly difficult to integrate into stable meaning because communication between cortical regions is no longer reliable enough to maintain coherent perception. Microvascular degeneration contributes heavily to this irreversibility by continuously adding ischemic injury to already vulnerable tissue. Each additional infarct removes more connectivity from networks already operating near failure thresholds. Cross-system interaction becomes destructive rather than compensatory. Cognitive fatigue worsens motor instability. Motor decline reduces physical activity, worsening vascular health further. Emotional stress increases inflammatory signaling. Sleep disruption impairs lymphatic clearance and metabolic recovery. The nervous system enters a reinforcing cycle where degeneration accelerates additional degeneration. Autonomic systems also become increasingly vulnerable during advanced progression. Heart rate regulation, blood pressure stability, swallowing coordination, respiratory rhythm, and gastrointestinal control all depend on intact brainstem and cortical integration. As connectivity deteriorates, basic physiological regulation weakens alongside higher cognition. At this stage, the brain is no longer struggling to preserve efficiency. It is struggling to preserve continuity of function itself. The emotional consequences become profound because fragments of awareness often remain intact during structural decline. A person may recognize portions of their own deterioration while simultaneously losing the ability to compensate for it. Frustration, fear, apathy, and exhaustion coexist inside a nervous system progressively losing regulatory stability. Eventually, reserve capacity disappears almost entirely. Recovery after stress becomes incomplete. Small setbacks produce lasting decline instead of temporary worsening. Functional baselines continuously lower because damaged systems can no longer restore previous performance levels. Irreversibility is not a single moment. It is the stage where compensation no longer meaningfully alters the outcome because too much structural architecture has already been lost. The visible symptoms at this point are not the disease itself. They are the exposed consequences of years of silent degeneration that the brain could no longer hide. By the late stages of neurodegeneration, failure is no longer confined to isolated symptoms. The nervous system begins losing the ability to coordinate entire physiological systems together. Movement, cognition, emotion, breathing, swallowing, cardiovascular regulation, and sensory interpretation start collapsing as interconnected networks rather than separate functions. The autonomic nervous system becomes increasingly unstable during this phase. Under healthy conditions, autonomic regulation operates continuously beneath conscious awareness. Heart rate adjusts automatically. Blood pressure stabilizes during movement. Breathing synchronizes with metabolic demand. Swallowing coordinates precisely with airway protection. These functions depend on uninterrupted communication between cortical regions, brainstem nuclei, peripheral nerves, and sensory feedback systems. As degeneration spreads through white matter and subcortical pathways, this integration weakens progressively. Swallowing dysfunction often reveals how dangerous system-level collapse has become. Normal swallowing requires exact sequencing between tongue movement, pharyngeal contraction, airway closure, esophageal coordination, and respiratory timing. Milliseconds matter because breathing and swallowing must alternate without overlap. Degenerating motor networks gradually disrupt this synchronization. At first, swallowing simply becomes slower or more effortful. Later, timing errors allow food or liquid to enter the airway. Aspiration risk increases because protective reflexes no longer activate with normal precision. The muscles themselves may still possess partial strength. The deeper problem is network timing failure between distributed systems that once coordinated automatically. Respiratory regulation also becomes vulnerable. Brainstem respiratory centers normally maintain rhythmic breathing without conscious supervision, while simultaneously responding to oxygen levels, carbon dioxide concentration, emotional state, speech demands, and physical activity. Neurodegeneration weakens this integration. Breathing patterns become less adaptable under stress or exertion. Respiratory muscles fatigue more easily because neural recruitment becomes inefficient. In advanced motor neuron disease, communication between cortical drive and respiratory musculature progressively deteriorates until ventilation itself becomes unstable. Sleep exposes these vulnerabilities further. During sleep, voluntary compensatory control decreases while automatic autonomic systems assume greater responsibility. Degenerating neural networks often struggle to maintain stable respiratory and cardiovascular regulation under these conditions. This contributes to fragmented sleep architecture, oxygen instability, autonomic fluctuation, and worsening overnight metabolic stress. Poor sleep then accelerates daytime cognitive dysfunction, emotional instability, inflammatory signaling, and fatigue, reinforcing the degenerative cycle further. Emotional processing also undergoes structural collapse during advanced progression. Earlier stages produced regulatory instability. Later stages impair the integration required to maintain emotional continuity itself. Frontal limbic disconnection weakens interpretation of emotional context, impulse filtering, and social synchronization. Emotional responses may become flattened, unpredictable, or disconnected from environmental reality because communication between regulatory systems has fragmented extensively. The person may still experience fear, sadness, frustration, or attachment internally while losing the neurological coordination required to express those emotions consistently outwardly. Isolation becomes one of the defining consequences of advanced neurological decline. Speech instability weakens communication. Cognitive slowing disrupts social interaction timing. Fatigue limits participation in ordinary activity. Emotional regulation becomes harder to sustain under stimulation. Externally, the person appears increasingly withdrawn. Internally, many remain aware of portions of the deterioration, while lacking the neurological stability necessary to maintain normal interaction with the outside world. Sensory systems also lose integration precision. Vision, hearing, balance, and touch may individually remain partially functional, yet the brain struggles to combine them into coherent environmental interpretation. Crowded spaces, rapid motion, noise, and complex surroundings become neurologically overwhelming. The nervous system begins prioritizing survival-level processing over higher-order integration. Basic orientation may remain possible, while multitasking, rapid adaptation, and environmental filtering collapse. Time itself changes during this stage. Earlier degeneration unfolded gradually enough for compensation to mask progression over years. Advanced decline compresses deterioration into shorter intervals because reserve capacity has already been exhausted. A minor infection may trigger permanent baseline decline instead of temporary worsening. A short hospitalization may accelerate cognitive fragmentation dramatically. Physiological stressors that healthy systems recover from easily now expose irreversible instability across multiple domains simultaneously. Cross-system interaction becomes destructive at every level. Reduced mobility worsens vascular circulation. Poor sleep worsens cognitive decline. Swallowing dysfunction increases infection risk. Respiratory weakness reduces oxygen delivery to already vulnerable neural tissue. The body and brain stop compensating for degeneration independently. Instead, failing systems begin amplifying one another continuously. At this point, neurodegeneration is no longer simply a disease affecting isolated brain regions. It becomes a full system coordination collapse where the nervous system progressively loses the ability to synchronize the organism as a unified whole. Consciousness itself may remain partially intact while integration disintegrates around it. The person can still experience moments of awareness, recognition, or emotional response even as communication between systems becomes increasingly fragmented. This mismatch is one of the cruelest features of advanced neurological decline. Awareness may survive longer than the nervous system's ability to express, coordinate, or act upon it effectively. The body still breathes. The heart still beats. Reflexes still operate in fragments. But the unified coordination that once allowed seamless interaction between thought, movement, emotion, sensation, and physiology is steadily disappearing. Late-stage neurodegeneration is not simply memory loss, paralysis, or tremor. It is the gradual collapse of synchronization itself across the systems required to sustain human function as a coherent whole. For years, the brain may already be failing before anyone realizes what is happening. Not because the damage is mild, but because the nervous system is designed to preserve outward function for as long as possible. Compensation hides degeneration behind routine movement, familiar conversation, automatic behavior, and temporary recovery. The person still walks, still speaks, still works, still remembers enough to appear normal. Meanwhile, microscopic structural failure continues spreading through white matter pathways, synaptic networks, vascular systems, and motor circuits beneath the surface. By the time visible symptoms emerge, the disease process responsible for them has often been progressing silently for a very long time. A delayed reaction, a missed word, a moment of imbalance, a brief mental blank during conversation. Individually, they appear harmless. Together, they may represent the first visible evidence that communication inside the brain is no longer fully stable. The danger of silent neurodegeneration is not only the damage itself, it is the delay between structural collapse and recognition. The slower the progression becomes, the easier it is for the brain to disguise what is happening internally. Neurons compensate for dying neighbors. Alternative pathways absorb failing signals. Frontal systems increase conscious control over actions that once happened automatically. Surviving circuits consume more energy to preserve the same visible behavior. The person feels tired, distracted, stressed, older, but underneath those explanations, the nervous system may already be operating near exhaustion. Small vessel disease slowly disconnects white matter communication. Demyelination destabilizes signal timing. Protein aggregation disrupts synaptic organization. Motor neurons lose the ability to sustain coordinated output. Memory systems weaken long before obvious forgetting appears. Different diseases, different pathways. The same final consequence. The brain loses synchronization with itself. That loss happens gradually enough that the transition can feel invisible while it is occurring. Human awareness depends on continuity. When decline unfolds slowly, each stage becomes normalized before the next stage begins. The new reaction speed becomes accepted. The new level of fatigue becomes routine. The new cognitive effort required for ordinary tasks becomes invisible through repetition. Compensation transforms deterioration into familiarity. This is why many people only recognize the progression in retrospect. They look backward after diagnosis and suddenly see years of warning signs that once seemed disconnected. The hesitation before movement, the increasing mental exhaustion, the imbalance during turning, the repeated conversations, the emotional instability under stress, the growing dependence on routine. The signs were present long before the collapse became undeniable. The most disturbing part is that the brain itself often cannot fully detect its own deterioration while it is happening. Systems responsible for judgment, self-monitoring, emotional regulation, and insight are vulnerable to the same degeneration affecting movement and memory. A damaged nervous system may continue insisting everything is normal, while structural stability is already disappearing internally. Then eventually, the compensation fails. The command is sent. Nothing moves. Not because the muscles forgot how to function. Not because the person stopped trying. But because the communication architecture required to transform intention into action has been progressively breaking apart for years. The visible failure is only the final exposure of damage that remained hidden beneath survival systems for most of its progression. That is what makes silent neurodegeneration dangerous. The brain can continue appearing functional long after the process destroying it has already begun.
Pathology of Fear is a medical documentary series presenting clinically documented neurologic and pathological mechanisms for educational analysis.